In this lesson, we are going to talk about different transformations that happen in rational equations and how that affects the graph between the parent function and the transformation. So speaking of parent function, think back to our quadratics unit that we completed. We talked about f of x as being my parent function. In quadratics, that parent function was x squared. And our transformation function, we added in the a value, the h value, and the k value. So these pieces here. So I've got the a value that's going to do something specific, h will do something, and k will do something as well. Now would be a really great time to pause the video. Go ahead and flip back to your quadratics unit. And this is also on your study guide. See if you can find the places where we talked about what transformations occur on a quadratic function. And I want you to use that to help you make some conjectures about what's going to happen when we look at these rational functions. So I am going to show you this. So that first equation at the top, that's what I'm going to use as my parent function, 1 over x. The reason that we call this a rational parent function is if you think of all of the exponent rules and the solving equations that we've done so far, a rational equation is when I have some type of variable showing up in the denominator. In this case, I'm using 1 over x as my parent function because I want to look at how adding different variables different numbers into the mix, like you see in your transformation function, how that affects the graph of 1 over x. So I have an app pulled up on my computer right now that we're going to use to help us determine what h, a, and k do to our graph. This is an app called Desmos. You can go to www.desmos.com and start graphing, and you'll be able to play around with these rational equations as well. You will have to type them in, but Desmos is an awesome tool that you can use to help figure out what type of manipulations are occurring for your parent function to your transformation. So you'll notice here that red is my parent function, 1 over y, y equals 1 over x. And what I've done here is I've put plus k, and it creates this thing called a slider. And what I'm going to be able to do, and you'll see in just a moment, is I'm going to be able to change the value of k using this slider and see how it changes my graph. Right now, k is equal to 0, which means that my parent function and my transformation function are identical. And I'm going to start changing my transformation function. So you'll notice as soon as I start to increase the value of k, something very special is happening to my graph. And I'm going to continue by sliding this down in the negative region. Take a second, pause the video, and I want you to make a conjecture about what k does to my graph and how you would verbalize that and explain that to someone else in class. So when I talk about these transformations, I'm going to be commenting or comparing these movements to the center of the graph. What I mean by the center of the graph is where that equation or where that parent function or that whatever function we're looking at, where it is currently centered. So if you look, right now I'm looking at the parent function. You'll notice that the x-axis and the y-axis are currently acting as bounding regions for this portion in quadrant 1 and this portion in quadrant 2. or excuse me, quadrant 3. So if you consider the axes, excuse me, of x and y as being your boundaries, where those two boundaries intersect, that's what I'm going to consider to be the center of my graph. So right now the center is at the origin, 0, 0. And as I increase the value of k, let's say I'm going to make k equal to 3, I have increased the values of y for my graph. So now instead of being bounded by the y-axis and the x-axis, I'm also going to add in a value here of y equals 3. So you'll notice that what I've just done is I moved my entire transformation function up 3 units, and I'm actually going to make this a dotted line. That dotted line there, let's make it green so you can see the difference. I have shifted my x-axis, which was my original bound, up now to being bounded at 3. So now I have the y-axis as one of my boundaries and the x-axis at the other boundary. So that's how I'm comparing my original function to my parent function. Excuse me, my original function to my transformation function. I've changed how that function is related to the y-axis and the x-axis by increasing all of the y values. So let's do the same thing, and now I'm going to look at a rational with a transformation with the h values. Gotta be extra super careful here when you're thinking through this in your head, because in the denominator it is x minus h. So if I'm looking at the h value of -3, my function is actually represented by 1 over x plus 3, because I would have minus a negative h value here. So whatever number I'm using here for h, it is resulting in the opposite for that h value in the denominator. So I'm going to take my slider. Right now, because h is equal to 0, I'm at my parent function. And if I increase the h values, now let's make this a whole number. Let's do h equals 5. This function that I'm looking at when I have an h value of 5 is actually 1 over x minus 5, because I am doing the opposite of the h value, as it tells me in the denominator here. Now, if I made this h equals -5, which would be represented with x plus 5 in my denominator, I'm moving over to the left. So for our intents and purposes, I'm going to say that h is equal to -2. Looking at the original, the x and the y-axis, in relation to how that bounded my parent function, I haven't changed the x-axis as being one of my bounds anymore. I've shifted the the vertical boundary, or what used to be the y-axis, and now it's actually at the value of x equals -2. And again, I'm going to make this a dotted line so you can see where that boundary is showing up. So now I'm bounded by the x-axis and this vertical imaginary line of x equals -2. So I've shifted the center of my graph from the origin over to the line created by the intersection of x equals -2 and the x-axis. So now my center would be right here at -2, 0. And the last thing that we're going to look at is how the a value changes my graph. So currently you'll see that my a value is equal to 1, because if I substitute in 1 into my transformation function, I would have 1 over x, which is my parent function. And here I am going to add in, I'm going to add in my boundaries, because what I want to do is I also want to be able to look at how the boundary is relating with that A value. So you'll notice now I have my dotted lines for the X and the Y axis. So look at, as I drag the slider to change the transformation function, think of how you could put into words what is happening with the function in relation to the boundaries that we've created with the X and Y axis and the center of the graph. So first thing I'm going to look at is when A is larger than 1, so a larger number than my parent function. And I'm increasing the A value, and you'll notice what is happening to the graph in relation to my center and those boundaries. And I'm going to bring this back to A equals 1 so that I'm back at my parent function. And the next thing I'm going to do is use the slider to bring this number closer to 0, but I'm not going to actually go beyond 0 just yet. So this is an example of when my A value is larger than 0, but less than 1. And now I'm going to manually change my A value to -1. What I want you to do before you come into class tomorrow is make a conjecture about what the A value is doing in relationship to the boundaries and the center of the graph. And the other thing I want you to start to think about is how would the domain change if I'm changing any of the A, H, or K values in my transformation function. And I also want you to take a look at the end behavior and make some conjectures about end behavior. When we come into class tomorrow, we're going to talk about what we saw in these graphs, and then we're going to start talking about these conjectures that you've made about domain and end behavior and A. If you'd like to play around with Desmos, the website is desmos.com. Show you what that looks like. So this is what it'll look like when you go to desmos.com, and you can click Start Graphing, just in case you're interested. So when you click on Start Graphing, it will bring you to a screen that looks like this. And then you can start typing in what you want to graph so that you can start looking at these functions as well. If you have any questions about the video, jot down a note in your notebook, shoot me an email if it's a super pressing question that you have to know the answer to tonight. I'd be happy to shoot you back an email. Otherwise, make sure that you have your conjectures ready for class tomorrow, and we will talk about them as a class.